So let's see some examples of this in action. The examples. Find power series representations of the following functions and state their radius of convergence. First example, g of x is 1 minus x squared under 1. Second example, h of x is equal to 1 over 1 plus x squared. Third example, j of x is ln of 1 plus x, so natural log 1 plus x. Fourth and final example, f of x equals arctan x. Okay, so at this point in the video, pause and see if you can solve these, and then I'm going to run through the solutions. Okay, so solution. 1. Consider p of x defined to be 1 over 1 minus x. Then the derivative of p of x is 1 over 1 minus x squared, which is equal to h of x. So, for absolute value of x less than 1, h of x equals the derivative of p of x, which is equal to the derivative of 1 over 1 minus x, which, and here's where we're using the assumption that the absolute value of x is less than 1, is equal to the derivative of this power series, which by the theorem is we just differentiate term by term, because that's what the theorem says, we can differentiate term by term. So theorem part 1. And we have found a power series representation for h. And here again is where we used absolute value of x less than 1. So r is equal to 1. Second example. In the exact same sort of vein, 1 over 1 plus x squared is equal to 1 over 1 plus x. The derivative is equal to, for absolute value of x less than 1, minus 1 to the n, x to the n, and it goes from 0 to infinity, take its derivative. And how do we take its derivative? We take its derivative term by term, using again theorem part 1. So minus 1 to the n times n, x to the n minus 1. And again, r is equal to 1. Okay, the third example is worked out in your notes, so see notes for that. Example 4, arctan x is equal to, well, it's the antiderivative, it's an antiderivative of 1 over 1 plus x squared, which is equal to integral. Remember, now this formula is going to be valid for absolute value of x less than 1. Integral of the sum minus 1 to the n, x to the 2n, from 0 to infinity. And what does the theorem say? It says we can integrate term by term. So we have our constant integration plus integrate term by term, minus x to the n, x to the 2n plus 1 over 2n plus 1. Now, how could you find that c? I'll leave that as an exercise. Try and find what the constant of integration has to be. Think what value of x could you plug in both sides to figure that out. So, remark, to find the interval of convergence, so we found the radius of convergence for each case, but to find the interval of convergence, we would need to check the endpoints. Remember, because it could be open, half open, or closed intervals. So what have we shown so far? We have the following power series representations of the below functions, the functions in this table, and we have the intervals on which the values of x make sense to plug into these power series. Where are these representations valid? Now there's a question mark above some of the inequalities, and that is because we haven't checked the boundary cases. So we don't know exactly the interval of convergence. You would need to check it. For example, in the second from the bottom, the ln1 plus x, you don't know if this will converge for x equals 1. So you need to check that individually. Okay. Similarly, for arctan, you don't know for either endpoints. Okay.